what do we do with matrices? Mostly we multiply them by vectors. There are two ways to multiply a vector in a matrix. One is called matrix vector multiplication, and the other is called vector matrix multiplication. For each of these, I'm going to give two equivalent definitions. And which definition is most appropriate depends on the situation. We start with the linear combinations definition of matrix vector multiply. So given an R by C matrix M, if V is a C vector, then the product M times V is the linear combination of the columns of M where the coefficients are given by the entries in V. So, for example, given this matrix and this vector, we take the product by multiplying the first entry of the vector by the corresponding column, the second entry of the vector by the second column, and the third entry by the third column. So we get this. On the other hand, if V is not a C vector, then the product M times V is not even allowed. So, for example, this matrix vector product is an error because the number of entries in the vector isn't the same as the number of columns in the matrix. Here's another example. The product of this matrix by this vector is obtained by taking this entry of the vector and multiplying it by this column of the matrix. This entry multiplied by this column, and this entry multiplied by this column. And here's the result. Recall the lights out puzzle. We said that a solution to a given configuration for lights out is a linear combination of the button vectors. And we can write a linear combination as a matrix vector product. For example, this linear combination, which expresses this configuration in terms of button vectors, can be written as the matrix vector product, where the columns of the matrix are the button vectors. And the vector specifies the coefficients in the linear combination. Solving an instance of lights out, therefore, can be expressed as solving a matrix vector equation. That is, given the desired configuration and given the matrix, find the entries of the vector such that the matrix times the vector equals that desired configuration. This is a fundamental computational problem, solving a matrix vector equation. The input is a matrix and a vector, and the goal is to find a vector x such that A times x equals B. Here's a way to solve the special case where the matrix is 2 by 2. To solve an equation of this form, we require that AD is not equal to BC. And if that's the case, we solve by setting x equal to dp minus cq over AD minus BC, and y equals AQ minus BP over AD minus BC. So, for example, to solve this matrix vector equation, we would set x and y according to the formulas. Later, we'll study algorithms for the more general case. We provide a module solver that defines a procedure, solve AB, that tries to find a solution to the matrix vector equation AX equals B. And currently, solve AB is a black box. Over the course of time, we'll figure out how to code it. Let's see how we can use it to solve lights out, for example. We start with 2 by 2 lights out. First, we create the domain for the button vectors. It's the Cartesian product of 0, 1 with 0, 1. Now we're going to create some vectors. So we better import the vec class. And these vectors will be over GF2. So we import the value 1 from the GF2 module. And now we're ready to make these button vectors. So first we'll create the button vector corresponding to the button in position 0, 0. Okay, here it is. Notice that it has a 1 in position 0, 0, 0, 1, and 1, 0. Next, we create the button vector corresponding to the button in position 0, 1. That has ones in positions 0, 0, 0, 1, and 1, 1. Next, we create the button vector for the button in position 1, 0. That has ones in positions 0, 0, 1, 0, and 1, 1. And finally, we create the button vector for the button in position 1, 1. And notice that this has ones in positions 0, 1, 1, 0, and 1, 1. Now we want to solve a 2x2 lights out puzzle. Starting from this configuration, with lights on in positions 0, 0, and 1, 0, which buttons do we have to push to get all the lights to go out? We formulate this as a matrix vector equation. The matrix has as its columns the button vectors. So the first thing we want to do is construct that matrix. We use call_dict to mat. The labels of the columns will be the positions of the corresponding buttons. 0, 0, 0, 1, 1, 0, and 1, 1. Our goal is to find the vector alpha 1, alpha 2, alpha 3, alpha 4, such that this matrix A times this vector equals the vector corresponding to this. So let's construct this vector. We'll call it B. It has ones in positions 0, 0, and 1, 0. Our goal is to solve a matrix vector equation, so we'll import the solve procedure from the solver module. We'll try to find the solution. All right, we came up with something. We don't yet know if it's really a solution. Let's test it out. A times x, is that equal to b? Yes, good. And here's the solution. It's a little easier to read off the solution if we print the vector. All right, so this tells us that the solution is to press the buttons at 0, 1, and 1, 1. That is, we press the button corresponding to this and corresponding to this. Vector matrix multiplication is different from matrix vector multiplication. Let's start with the definition of matrix vector multiplication. Remember, it's the linear combination of the columns of the matrix with coefficients given by the entries of the vector. Here's the definition of vector matrix multiplication. To multiply a vector W times M, you take the linear combinations of the rows of the matrix M with coefficients given by the entries of the vector. So, for example, multiplying this vector by this matrix, we take the linear combination of the two rows with coefficients equal to the entries in the vector. You remember our Junko example from a while back. Junko makes a bunch of products, and for each one uses a certain amount of each of these resources per item. We can write this data as a matrix. Now, the total resources used equals this vector times m, where the entries of the vectors tell us how many of each item are being manufactured. Recall that in industrial espionage, we might want to calculate how many of each item Junko is produced, assuming that we know the total resources used, and of course, we know the matrix M. To find the number of items produced, we would solve a vector matrix equation, B equals x times m, where B is the vector of total resources used. So again, solving a matrix vector equation is a fundamental computational problem. And of course, if we had an algorithm for this problem, we could use it to also solve a vector matrix equation just by using the transpose. When using the solver module to solve equations over the real numbers, we have to be aware that Python is using floating point numbers, floats. So round-off errors occur. For example, 10 to the 16 plus 1 is equal to 10 to the 16, according to Python. So algorithms such as that used in the solve procedure, don't find exactly correct answers. So to see if the solution obtained by the solver is a reasonable solution to the matrix vector equation, we see if the difference between the target vector B and the vector A times U has entries that are close to 0. So these entries are very close to 0, so we consider that a success. We've found the solution. Now, this vector, the difference between B, the target vector, and A times U, is called the residual of the matrix vector equation. An easy way to test if the entries of the residual are close enough to 0 is to compute the dot product of the residual with itself. In this case, the dot product is this tiny number. So we're pretty confident that we've gotten a solution to this equation.
Let's go ahead and use the solve procedure to solve the industrial espionage problem. It involves solving this vector matrix equation. So first we have to construct the matrix itself. We import the mat class. Now, the row labels of our matrix will be the products, and the column labels will be the resources. And now I'm going to actually construct that matrix of data. Next, suppose that this vector specifies the observed resource utilization, 1409.5 units of electricity, and so on. We want to solve this vector matrix equation. We use the solve procedure. The solve procedure expects to solve a matrix vector equation, so we have to transpose the matrix. Now let's look at the solution. All right, it looks like 1,000 gnomes were produced along with 175 hoops, 590 silly putties, 75 salad shooters, and 860 slinkies. Should the fact that these values are integer give us some kind of confidence in the solution? Well, perhaps, but let's look at the real entries of U. You can see that the print procedure did some rounding. Let's just see if the solution makes sense by multiplying U by M and seeing if the result looks anything like B. All right, plastic, 677 was what we observed, and this gives us 676.9999, and so on. So it's pretty good. Let's compute the residual, in fact. Now, compute the dot product of the residual with itself, and it's this very tiny number. So we're convinced that the vector U is, in fact, a solution to this vector matrix equation.
Now, for some matrix vector equations, there is no solution. And in this case, the dot product of the residual will not be so small. That'll indicate that the vector we got is not a solution to the equation. And in this case, there is no solution. And we'll learn later that the algorithm used here actually computes a solution that's, in a sense, as close as possible, so that the residual is, in a sense, as small as possible. Some matrix vector equations are ill-conditioned, which means even if there is a solution, we won't be able to get it using the solver. So this is an example where there's a solution, but the residual is quite large. We're not going to study conditioning in this course. To learn more about that, study numerical analysis.